Let's look at one more example with LaGrange multipliers in 3 dimensions. I think the algebra on this will help you to sort of see how to set these things equal and then how to solve for the different lambdas to find out what the maxes and mins are. So this is a little bit of a funky application problem, right? I've got a point on a plane, and I want to find the point on that plane that's closest to the point -2, 5, 1. Now, the first note I said is the point's not on the plane. If you start putting a -2 in for x, a 5 in for y, and a 1 in for z, you're not going to get 0 on the other side. So what you've got is you've got some sort of a plane and then a point that's somewhere away from that plane. And you want to find the point on that plane that is closest to this point in space. If you want the distance formula for 3 dimensions, that's the distance formula for 3 dimensions. Difference of the x's squared, difference of the y squared, difference of the z squared. Add them up, take the square root. Now, you want to minimize the distance, but we can make our life a little bit easier by minimizing the square of the distance, because whatever minimizes the distance will minimize the square of the distance as well. In other words, that distance is the objective function, and the plane is our constraint curve. So this is our objective function, right? This is our z, and this is our constraint curve. This is our g of xy. So we're trying to minimize distance constrained by, or subject to, I should say, that plane. Okay, here's how this looks. First of all, if we want to write the objective function, we can do it like this. The point we were given was -2, 5, 1. So the distance is going to be equal to x minus a -2 squared plus y minus 5 squared plus z minus 1 squared, right? If I wanted to really find distance, I would take the square root of this whole thing, but really we said we can maximize the square of the distance and we'll be okay. Great. Now what? We need partial derivatives. So this thing is the f function. So the derivative of f with respect to x is just 2 times x plus 2. No chain rule necessary. The derivative of the inside is 1. Partial with respect to y is just 2 times y minus 5. Partial with respect to z is 2 times z minus 1. Now, go back to the objective function, and you find out that the partials there are all constants. The partial with respect to x is just 2. That's the coefficient of the x. The coefficient of the y is 3. The coefficient of the z is 6. All right, so f equals lambda g. Let's start setting up our gradients and the equations that come out of those gradients. So the first one looks like this. 2 times x plus 2 equals lambda times 2. Not bad at all. 2 times y minus 5 equals lambda times 3. 2 times z minus 1 equals lambda times 6. So will I get any fun, interesting equations like I got last time? I don't know. Let's try solving all these for lambda. So if I divide everything here through by 2, I end up with x plus 2 is equal to lambda. Okay, hold that thought. Over here, if I divide both sides by 3, then I get 2y minus 10 over 3 is equal to lambda. And over here, if I divide everything through by 6, I get z minus 1 over 3 is equal to lambda. So now I've got lambda equals 3 different things, and basically I want to go back and I want to set equations equal to each other with the hopes of solving for one variable in terms of another. So look at my 3 red lambdas up there. What can I do with them? Well, the first thing is, let's try setting equation 1 equal to equation 2. If lambda is x plus 2, and lambda is also 2y minus 10 over 3, maybe there's some interesting relationship that can come out of them. All right, hit both sides with a 3, and I get 3x plus 6. On this side, I get 2y minus 10. So maybe I can solve for y. add a 10 to both sides, and divide by 2. And I get y equals 3 halves x plus 8. All right, so now I've got y in terms of x. That's pretty good. What if I could get z in terms of x? That might be helpful. The third one is the one that has a z. The first one is the one that has an x. All right, so let's set equation 1 equal to equation 3. So equation 1 is lambda equals x plus 2. On the other side, it's z minus 1 over 3. So multiply both sides by 3. This is starting to sound familiar. 3x plus 6 on this side. Z minus 1 on the other side. Oh, add a 1 to both sides. And I get z equals 3x plus 7. Now, I've got to take those y's and z's and substitute them into my constraint curve. Okay, so substitute these into g of x, y. Somewhere on a paper, I hope you have the original g of x, y. It goes like this. 2x plus 3 times y, which we now can write as 3 halves x plus 8, plus 6 times z, and we can replace a z with a 3x plus 7, minus 10 equals g of x, y, or really equals 0. All right, 2x plus 9 halves x plus 24 plus 18x plus 42 minus 10 is 32 equals 0. Let's solve for x. 18 and 2 is 20. If I add 20 plus 9 halves, that's the same thing as saying 40 halves plus 9 halves. So 49 halves times x. And then 24 plus 32 is 56. Okay, move things over and solve. So if I move the 56 over, I end up with 49 halves x equals negative 56. And then for my next trick, I'll multiply both sides by 2 over 49. Because that'll clear out that 49 halves on the left-hand side. When I'm all done, I get an x on this side. There's actually a common factor of 7. Gives me x equals negative 16 over 7. Now what is y? Y is 3 halves x plus 8. So y is 3 halves times negative 16 over 7 plus 8. Well, that'll just give me an 8. I get 24 sevenths plus 8 more, ends up being 32 sevenths, right? Because this will give me a negative 24 over 7. 8 times 7 is 56 over 7, so I'll end up with y equals 32 over 7. And then what is z? Z is equal to 3x plus 7, so 3x plus 7. Negative 48 plus 49 is 1, so I end up with a 1/7. Now, here's what you have to do. Take this point, x equals negative 16 over 7, y equals 32 over 7, and z equals 1 over 7, and put it back into the original function. I don't mean to steal the suspense, but I already did it. And when I did, surprisingly enough, it comes out to be exactly 1. So what does that mean? That means that the point that's closest, the closest point to the plane, is the point negative 16 over 7, 32 over 7, 1 over 7, and it's 1 unit away. of whatever distance measure you're using. Now, here's a question. How do I know that that's the closest point? How do I not know that that's the farthest away point? In other words, how do I know that I just found a minimum instead of a maximum? Because I didn't run any kind of special test to figure out. Well, work your way through. That has to be the minimum because the maximum is infinity, right? The maximum is I pick a point as far away as possible from that given point, which is an infinite distance away. So that's how I know that it has to be the closest point. But you do want to think for a second, well, gee, how do I know it's the closest? Because one unit has to be the smallest value, infinity is the largest. And that's the end of LaGrange, and that's the end of chapter 15.